In this video, we're going to apply compositions of transformations. In other words, we're going to perform combinations of two or more transformations. The first one will be a translation followed by a reflection, called the glide reflection. It looks something like this. We take segment PQ, we translate it up several units to PQ prime, and then reflect it about a line to get our final image, PQ double prime. That line of reflection is parallel to the line of translation. Another example is triangle ABC. We are going to do a glide reflection, translating it 12 units to the left first, and then reflecting about the x-axis. So here we go from our blue triangle ABC to our red triangle ABC prime, where all of the x-coordinates are 12 less than what they were originally. And then we flip to the third quadrant here to our green triangle ABC double prime, where all of our y-coordinates are now the opposite of our ABC prime. Trying another example, let's take our triangle ABC and translate it 4 units down, and then reflect about the y-axis. What are the coordinates of our new image? Here we have ABC prime in red. Note all of our y-coordinates are 4 less than what we started with. And then we reflect about the y-axis, and note all of our x-coordinates are the opposite of our ABC prime. Our final image is here in green, ABC double prime. What would happen, or how would we describe, a glide reflection from ABC double prime to ABC? Well, here's ABC double prime in quadrant 3, and we basically do the opposite of what we did in our first example. We slide our triangle 12 units to the right. In other words, we add 12 to each of our x-coordinates and end up here at ABC prime in red. And then we reflect about the x-axis and end up here in the first quadrant with our original triangle ABC and original coordinates. So what does that mean? Well, it means that when we perform two or more transformations combined into a single transformation, the result is a composition of transformations, and that a glide reflection is an example of that. And these transformations are isometries. The final image is congruent to the pre-image. That leads us to this theorem, the composition theorem. The composition of two or more isometries is an isometry. An isometry is a rigid motion of a planar space, and the resulting image is congruent to the original image. Let's try one more. Find the image of a composition of a segment RS after we reflect in the y-axis and then rotate 90 degrees about the origin. Well, we might need a little refresher on the coordinate rules for rotations about the origin. When a point AB is rotated counterclockwise about the origin, the following is true. So our coordinates AB or XY are going to swap places in a 90-degree rotation, and your X coordinate will now be negative, or the opposite of what it was. So here is the example we were given. We take our S, which is here in blue, and we reflect it about the y-axis and end up over here in red at RS prime. And so notice that our y-coordinates are the same. Our x-coordinates are now negative in the third quadrant. And then we rotate 90 degrees over here to the green image, RS double prime. And now you can see between R prime and R double prime, the x and the y have swapped, and now the x is positive instead of negative, and the same goes for s. So compositions of two reflections result in either a translation or a rotation, as described in the following theorem. Reflection in parallel lines theorem, if we have lines K and M and they're parallel, and we reflect in line K followed by a reflection in line M, it's the same as a translation. In other words, a glide. So line PP, or line segment P double prime, is perpendicular to the lines we reflected about, K and M, and the length of P double prime is twice the distance between the two parallel lines, so it's 2D. So whatever the distance is between lines K and M, the distance from P to P double prime is twice that. This ends the first segment of compositions of transformations.